Welcome dear viewers to the another video on pharmaceutical analysis. This video is related to gas chromatography. It is a technique for the analysis of the residual solvents mainly in the pharmaceutical industry. In this video we are going to walk through the principles, components, applications and significance in the pharmaceutical analysis for the gas chromatography technique. It is called as GC mainly, and it is much applicable in the pharmaceutical field including the APIs, raw materials and the finished formulations. So gas chromatography is a analytical technique which is used to separate, identify and quantify the compounds that can be vaporized without decomposition, and these are the solvents mainly. This GC technique is used widely for analyzing the volatile organic compounds, residual solvents and impurities in the pharmaceutical samples. These are also used for the environmental analysis, food and flavor testing. The basic principle for the GC is GC works on partitioning of the analytic between the mobile phase, that is inert carrier gas, and stationary phase, that is liquid or solid. So GC works mainly on the principle of partitioning of the analytes in the mobile phase and the stationary phase. As it is a chromatography technique, it works on the principle of partitioning. Depending on to the affinity, the partitioning happens. GC use the mobile phase, that is inert gases. Stationary phase is liquid or solid coating inside the column. So when the sample is injected, it is vaporized and carried by the inert gas. The inert gas is the mobile phase and it may be helium or nitrogen. Each compound interacts differently with the stationary phase, that is with different retention times, and based on that the separation happens. Main components of GC: first is carrier gas, mobile phase, transports analytes through the column. Common gases are helium, nitrogen and hydrogen, and these carrier gases or mobile phase must be pure and inert. Second is injector, which introduces the sample into the system. Sample may be liquid, gas. It is vaporized in a heated injection port, and injection modes are there: split mode and splitless mode. So split mode for the concentrated samples and splitless mode for trace analysis. Column, that is a stationary phase. Two types of columns are there: packed columns and capillary columns. Packed columns contain the solid support coated with the liquid phase, and capillary column are long, narrow, coated internally. These are the modern GC systems equipped with the capillary columns. Stationary phase is a non-polar or polar polymer selected based on the sample size. Oven, it maintains the column temperature. Then modes of operation: so isothermal mode, in which there is a temperature programming. Then second is the detector. Detector detects the compound as they exit the column. Modes of operation are isothermal, that is with the constant temperature, and another mode of operation is the temperature programming. So if you program the temperature, then it is called as program temperature mode of operation, and in this gradually the temperature is increased for better separation of components. Detector detects compound as they exit the column. Common detectors are FID, TCD, PCD, MS. FID is flame ionization detector for the hydrocarbons, organics. TCD is thermal conductivity detector, which is for the gases and general use. ECD is electron capture detector. It is for halogenated compounds. MS is mass spectrometry for the molecular identification in the GCMS. So GC can be coupled with the MS, that is called as GCMS. Like LCMS, here it is GCMS. Then data system. So this data system converts detector signals into chromatogram. The retention time and peak area help in the qualitative identification and quantitative determination. That means the retention time and the peak area will give you what is present and how much is the present. Coming to the applications of the GC, so this is used for residual solvent analysis as per ICH Q3C guidelines. We need to specify and we need to check the residual solvents. Purity testing of volatile substances, identification of unknown impurities, quality control of raw materials, stability studies for volatile degradants. Advantages of GC: this technique is with high sensitivity and resolution. Fast and efficient analysis is possible with this. It is ideal for volatile compounds and it provides accurate qualitative and quantitative results. Some limitations are also there, like it is applicable only to volatile and thermally stable compounds. Non-volatile compounds require derivatization to make them volatile. So as per my understanding and my experience, generally the non-volatile compounds require the derivatization to detect through the GC, and the volatile components are very much easy to test and analyze by the use of GC. Then column contamination can affect the reproducibility and accuracy. So column contamination is required to be restricted. Purpose in the pharmaceuticals, like residual solvents are used in the pharmaceutical field, like class 3 solvents are generally used, some class 2 are also used. So whenever these are used, these are required to be reduced to the safe level as per the ICH guidelines, and these are required to be tested. So some examples for the residual solvents are ethanol, methanol, dichloromethyl, methane, acetone, and some others. So the testing by GC is required to ensure the compliance with the ICH Q3C residual solvent limits. These limits are given generally in the ppm. GC is a precise method, powerful method, and rapid analytical method or technique to detect the solvents and volatile substances. This plays the crucial role in pharmaceutical quality control and regulatory compliance, and it is essential for detecting impurities and ensuring the product safety. This is the information for the GC, and in upcoming time I will be making videos on the analytical instruments and analytical techniques for the pharmaceuticals. Thank you for watching the video.